Good afternoon. I'm Arun Serafin, the Executive Director of the Emerging Technologies Institute at the National Defense Industrial Association. I want to thank all the attendees for your support of NDIA and ETI and for joining us for today's webinar, Batteries 101 with Sam Gillard. This webinar is part of our Tech 101 series, where we present complex technological concepts as introductory webinars with a focus on their national security implications. We all know that batteries are everywhere in our daily lives, powering our cell phones, our tools, even our cars. For the DoD, these batteries are mission critical, enabling key platforms and applications across the force. As the demand for this technology continues to grow, understanding how batteries work, how they fail, where they're made, and the unique design and supply chain challenges for defense applications becomes increasingly important. Yet, we often take them for granted and rarely stop to consider the complexities behind this essential technology. Today's webinar provides an overview of battery technologies, including fundamentals of operation and a survey of battery technologies for use in a wide range of defense and civilian applications. Some administrative remarks before we get started. First, all attendee lines are muted. Second, if you have a question during the webinar, you can submit your question in the question box in the webinar panel on the right side of your screen. You can submit questions during the presentation throughout. We'll do our best to get through all the questions at the end during the Q&A portion of the session. We are recording today's webinar for members unable to attend and for any member who wishes to review the materials at a later date. Within the next few days, we'll also post the slides and the recording to our website and our YouTube channel. With that, I want to introduce our speaker, Sam Gillard. Sam is the Vice President of Strategic Marketing Innovations, SMI. Prior to joining SMI, Sam spent 6 years at the Department of Energy, most recently as the Technology Development and Supply Chain Manager for the Vehicle Technologies Office and the Manufacturing and Energy Supply Chains Office. He's also worked on DOE's battery supply chain program. He's overseen an SBIR portfolio for battery technology and performed technical reviews for various DOE programs. Sam previously served in the United States Army as a signals intelligence analyst. He's also worked at NSA and served in Afghanistan during Operation Enduring Freedom. Sam holds a Bachelor of Science in Material Science and Engineering with a specialization in nanotechnology from the University of Maryland at College Park. Sam, thanks for joining us today, and I'll turn it over to you for your presentation.
Great. Thanks, Arun. It's good to meet everyone. Sam Gillard, as Arun said. I'm just going to hop right in. I have a ton of stuff to cover, so I will go ahead and get started. Is everyone seeing my screen okay?
Good.
All right, great. So yeah, today I'm going to cover lithium-ion batteries and sort of what the basic functions are, what the materials are, how they work, why they're chosen, and I'm going to cover some basics of lithium-ion battery manufacturing and the lithium-ion battery supply chain, and finish up with some of the more recent and relevant policies that are going to have some wider impacts on the North American market. Let's start with just how the lithium-ion battery works. So I promise not the rest of this is going to be via animation, but I love this animation, so I'm going to use it. The way lithium-ion batteries work is you have a shuttle between the anode and the cathode as it's charged and discharged. What's happening here is the electrons go from one side to the other, and that releases lithium ions, which allows for the lattice of each side to hold on to lithium ions. This is a pretty regular, process, very well understood at this point. But lithium-ion batteries get their name because the lithium ions are the charge carrier going back and forth between anode and cathode. But they're only about 5% weight of the lithium-ion battery. Most of that weight is in the other materials. Specifically, in this case, it's in the cathode and anode. That's where the majority of the weight is. and a variety of materials make that up. So nickel, cobalt, manganese, aluminum, iron, and phosphate or phosphorus material. And then on the anode side, you have graphite, titanium, and next-gen materials is silicon and lithium metal. So I'll cover these in more detail in later slides. So the biggest thing that you need to understand about batteries is that material design choice in electrode and design choice really dictate from a performance level, from the battery at the material level to the electrode level, all the way up, really dictates how the battery is going to perform for rate and energy density. So rate is how quickly you can discharge and charge a battery. And then energy density is how much capacity that battery holds. So a lot of this is really balancing those end of life things. So if you look at this area here, this is commonly used. It's called a spider chart. And you look, different chemistries have different properties. And ultimately, it's all a balancing act, right? So if you want to change your power, you need to use a thinner electrode. Or you need to use a more porous electrode, which allows for lithium ions to intercalate at a faster rate, but there's less active material for you to intercalate into. So that's really, again, at the end of the day, that's really what it comes down to on a materials base or on an electrode basis. On a materials basis, what ends up happening is there is a direct relationship between surface area of that particle and the other material properties, in this case, the lifetime of that material. So we always call this the meatball, which is you have these primary particles which agglomerate into a secondary particle, and the higher surface area, the more it comes in contact with electrolyte, which allows for faster lithium ion intercalation, which means getting the lithium ions into the material. But what ultimately ends up happening is you have higher engagement with the electrolyte, which causes different species to form on the surface of that material and dissolution of that material into the electrolyte. So again, as I said, it's always a balancing act between what you want from a lifetime perspective, what you want from energy density, and what you want from a rate capability. So they're doing a lot of work as well to try to get the best of both worlds, right? To have a material that allows for the better material properties for just the coating. So they're doing atomic layer deposition and other materials tricks essentially to create a way for you to protect the core material from all of these negative impacts of lithium-ion battery technology. So cathodes, we'll go into in more detail now. So really at the end of the day, the biggest things you need to understand about cathodes are that they're typically some version of a transition metal oxide on your periodic table, and there are a number of them that are commercially viable. This is really primarily what drives design choice for DoD, for consumer electronics, for electric vehicles, all of the above. It's a cathode driven decision a lot of times. And so, as I mentioned before, with this, sort of design trade-off, each of these has different positives and negatives. So if you look at consumer electronics batteries, it's typically lithium cobalt oxide, which was the first cathode material discovered by John Goodenough in the 1970s. That's still being used widely today. And then you have the NMC material. It started with NMC 111, which is nomenclature for 1/3, 1/3, 1/3 of nickel, manganese, and cobalt. So that transition has gone from 111 to 622. Next gen is 811, and then even 90% nickel. So these are essentially the ratios, and the higher the nickel content, the higher the capacity, and more importantly, the less amount of cobalt. And cobalt I'll cover in a little more detail to give you an idea of why you need to try to get cobalt out of the battery, but ultimately it's fairly difficult. In DoD applications, typically you see NMC, but LFP is becoming more common. In defense applications, a lot of it is the demand for the domestic supply chain is driven by EVs. So in what's available a lot of times was NMC. Now that's transitioning more to the LFP regime, but I think the prevailing wisdom is that it's going to be both in the future. So anodes, the very first anode that was used for batteries at large scales is graphite. Graphite still exists today and is still the primary material that you see that's being used in lithium-ion batteries. So this, I actually have a tool. This is an atomic model for graphite. Graphite is a series of graphene planes. So that those that don't know about graphene, so basically there is a picture almost chicken wire, right? And each of these is very strong in this planar direction, but it is very easy to shear in this direction. And that's because the bonds between each layer is very weak. And that's why you could write with a graphite pencil, and that graphite pencil sheds off essentially and comes off. That's the focus. But the way that it works with lithium-ion batteries, the graphite material in each of these 6 graphite hexagonal, crystal formation, you have a space for a single lithium ion. And so for every 6 lithium ions, or for every 6 carbon atoms, you have a single lithium ion. So this goes through as it's filling up. It actually starts as a black material, and then as it fully intercalates and charges, it actually changes into this really pretty gold material. Actually, it's really cool. And so graphite, there's 2 types of graphite: natural and synthetic. Natural has the advantage of being lower cost, although that delta is shrinking as synthetic graphite has become less expensive. But natural graphite is higher capacity. And the reason for that is the graphene planes in each natural graphite are larger. And so when you look at the way that ultimately looks inside of a particle, kind of looks like this. So if you look at a graphite plane or a natural graphite plane, it's going to be longer, which allows for more lithium to go into it. And synthetic graphite tends to be a little shorter, like that, and that's more predictable. But it also is better lifetime material and better rate material. So what you see in industry these days is sort of a trade-off between natural and synthetic, and they use kind of a blend a lot of times. The other important part about anode materials is the solid electrolyte interface. This is a really important aspect, which is the reason why graphite is still ubiquitous, even though graphite is not near as high capacity as some of these other materials. So when you charge and discharge a battery, you need to have this layer which is able to create a barrier so that your anode material doesn't dissolve into the electrolyte. Graphite's great at this. Other materials, next-gen materials for batteries, are less so. So the next gen material here is silicon anodes. So instead of 6 carbons needing a single lithium atom, you have 1 silicon atom, which is 4 lithium atoms that go into that crystal structure. What ultimately does with that is it causes expansion of that material 3 times, about 3 times when it's fully charged, which causes an almost breathing effect of that silicon material, which is causes a sort of pulverization of that material, so causes surface area to increase over time, which increases the connection points between the electrolyte and the silicon anode, which causes early decay. So even though they're very much higher capacity, you have calendar life issues partially because of the expansion of that material in the electrolyte during cycling and of the battery. Then you have the lithium metal anode, which is essentially no host material on the anode side. It's just lithium metal, which causes it to plate and strip on the surface of the current collector. When you have that material, what ends up happening is you have a uneven discharge and charge over time, and that causes dendrites, or these lithium metal spheres essentially that can connect both sides through the separator, which causes a discharge, which causes thermal runaway, which causes battery fires. So next up, we have the inactive materials. So I'll run through these really quickly. You have the electrolyte, which basically its role is to shuttle lithium ions back and forth. This is a very closely held secret in industry in terms of what salts are used and at what distribution and what blends. So you have a carbonate material as your solvent, and then you add salts in different degrees. LiPF6 is what's used by and large, but you have a lot of these other additives which create things like low temperature performance, better thermal stability, safety response, things like that. Low temperature performance specific to DoD. This is an area where industry is not typically in the temperature regimes that you need for the DoD applications. They need to typically go to -40 degrees Celsius, and that's not necessarily needed for electric vehicles. So a lot of the development in low temperature side is driven by DoD in this particular case. Next, you have the separator. The separator is used to isolate electrically between the cathode and the anode. So as I mentioned earlier, with respect to the dendrites forming from anode to cathode, that creates a short, which allows for an electrical bridge between anode and cathode when you have a dendrite that's electronically conductive, like lithium metal. But ultimately, you basically use a polymer-based material. That polymer-based material allows ions to flow, but does not allow any electrons to flow through. Next gen material is typically ceramic coatings and other polymer blends, but ultimately, the separator is the separator. A lot of the advancements come in manufacturing innovation. The other parts that are inactive materials, and when I say inactive, it means it doesn't hold charge and it doesn't hold material for charge and discharge. So binder and conductive additive, these are added during the slurry process, which I'll go through in a bit. But this sort of forms a matrix in the electrode, which allows, and for binder, it allows the particle-to-particle adhesion, which allows for batteries to be able to charge and discharge throughout the thickness of the electrode. Next, you have conductive additives. These allow for electronic conductivity through the electrode, which allows for faster charge and discharge. You can add more of this material, both active material or binder and conductive additive, but you're trading off energy density because the higher any of those numbers are, that's lower numbers for active material. That's across the board for pretty much anything non-active. So most of the design in lithium-ion batteries is pushing for as much of the material composition to be inactive, for it to be active material. So next you have current collectors. Current collectors on the anode side, you have copper. This is typical for the material. They're less than 10 microns. I believe it's about 8 microns today. There's some really cool work in non-porous or in porous current collectors, which allows for thinner electrodes and less material to be used. Aluminum current collectors are in the cathode side, and the role of the current collectors are to collect electrons. and shuttle back and forth during charge and discharge through whatever work is being done with those electrons. So I'm going to cover lithium-ion battery manufacturing. Anyone has any questions about the how lithium-ion batteries function, I would be happy to answer at the end. But we'll start with why it matters on lithium-ion battery manufacturing. And specific to DoD, there's a number of challenges with lithium-ion battery manufacturing and why it's hard for DoD to source material, and ultimately why EVs and decoupling EVs and the defense industrial base for batteries are very challenging. So you want to be able to find a commercial application as well as a DoD application to sort of match that demand. So if you look, as technology grows, there's a huge delta between the EV light duty market and the other markets, so consumer electronics, medium and heavy duty. This gap has gotten bigger and bigger over time. And so if you look, what was 15 years ago, state of the art for light duty was a 2 gigawatt hour facility. Now it's 25 gigawatt hours plus, essentially, to be commercially viable at that cost. But smaller than that, you have the consumer electronics side and medium and heavy duty trucking. That's going to be a growing segment over the coming years. And then everything else, DoD, is below that 1 gigawatt hour demand. I think if you aggregate all of DoD demand, it's less than 1 gigawatt hour. And so it's a very small part of the market, but obviously very important part of the market. So you have some of the DoD larger programs like the 2590, the 6T battery, and the CWB. A lot of battery programs have specialized battery needs, but I'll cover a couple of those in a few minutes. Next, you have some of the specialized applications, so kind of one-off designs that are required because of the fact that maybe it's a form factor that doesn't quite work with larger scales, and or it's got a unique environmental requirement, like a lower temperature than even larger design or things like that. And then you have some of the niche markets, consumer electronics markets, and drones. When I managed the SPIR portfolio, I always pointed people into the drone market because it's a very, folks are willing to spend a higher amount per kilowatt hour since the batteries are small and the cycle range is typically lower. So overall, the way batteries are made, you have a slurry preparation process, coating and drying, calendaring, cutting electrodes, and cell assembly, and then you fill it with electrolyte and formation of the battery. So slurry formation, what you have is an agglomeration, a suspension of liquid that is a mixture of active material, conductive additive and binder, and a solvent, which allows for these particles to be separate, but also create a matrix that can coat onto the surface of that current collector. From there, this is a major area for differentiation. This is also driving a lot of what ultimately creates upper bound limits for thickness of electrodes at commercial markets. It's harder to get thick electrodes in a slurry-based process, and I'll cover why that is here in a minute. But ultimately, this is one of the most coveted positions in lithium-ion battery manufacturing, and where some of the deepest sort of institutional knowledge company to company exists is in the rheology and slurry production. Next, you have calendaring. So drying that material. This is where you see the impacts and benefits of scale. So what needs to happen is that once that coating is coated, or once that electrode is coated, then it needs to be dried and compressed during the next phase once it's a liquid on the electrode. What you see here is I believe it's a 1 megawatt hour line. This is a 6 gigawatt hour line. This is what's commercial in today's market. And this obviously is a huge difference in terms of capital costs, and ultimately also quality. And that's one of the things that is interesting here is the tolerances, even though the scale is larger, the tolerances for manufacturing are typically even smaller at these scales, which is why the performance targets for a lot of the light duty vehicles versus some of the other smaller scales are typically less rigorous. Uh, and so the more automated you can get with your lithium-ion battery manufacturing, the better off it's going to be. So the reason why these are long, and when I say long, I mean 100 meters is pretty common for a piece of drying equipment. This is really what takes up the most space in these huge facilities, is because they use convective heating. And that is essentially just like an oven, right? You heat that material, it needs to get deep enough to fully dry before going to that next stage. So there's a lot of interesting work going on in advanced heating technology, so microwave heating, which is exactly the way it sounds, except in this case, you're varying the frequency of the microwaves, which allow for that microwave to dry in a uniform way. So next we have next we have cutting electrodes and cell assembly. So what happens once you have these major drums of material is you need to take your anode and your cathode, and you need to add separator to that. There's different ways that you're going to see these wound. You have Z stackings and prismatic winding, single sheet stacking. Depending on the form factor of the battery, so the major types of cells that exist, you have cylindrical cells, which is what the Tesla uses, which is what a lot of DoD application uses. And the typical format is 18650, 26650. All of these numbers equate to the first two being the diameter of that material, and then the next two are the length of that cylinder. So 18650 is 18 millimeters by 65 millimeters. And so the other ones are pouch cells, and then you have these hard cell prismatic as well. But essentially, you have these different types of stacking equipment that needs to take the anode and cathode and separate the separator, and then ultimately puts that in a hermetically sealed or inside of a cylinder, or inside of a can, they call them, and then they fill it with electrolyte, which I'll cover here in a minute. But the design of the cell is really important in how the cell performs. So a larger cell with a high surface area, that's going to dissipate heat easier. And so there's going to be a lot of other things at the cell level that you're going to have to think about as you do your cell design. DoD is doing a lot of work on standardization because you need specialized equipment for these different form factors. And so this is the stub battery. DoD is trying to get as many batteries as possible to utilize the same cells, which allows for industry to have a demand signal that allows for it to create enough demand for them to get sort of these next gen and better cells, and ultimately, as you'll find later, to move away from the battery supply chain, or sorry, move away from the Chinese supply chain. So next you have the electrolyte filling station. So that's exactly what it sounds like. You take these wound electrodes and you fill it with this electrolyte mixture. Then what happens at that point is the electrolyte, it goes through a gassing phase. So you don't seal it right away. You allow for it to off gas, and then you seal it. And then from there, you go through what's called formation, which is a slow charge and discharge process in a temperature controlled environment. This is a huge driver of lithium-ion battery manufacturing costs. These things are, in this picture, you're looking at, 75 feet or something to that effect, right? So these very, very large chambers. It typically takes over 10 days to form a battery. in these commercial scale facilities. So major cost driver for folks that are interested in research in this space. Shortening electrolyte formation time is a huge interest to industry. All right, next I'm going to cover the lithium-ion battery supply chain basics, why it's important and why it's important to DoD. So I call this one the we're going to need a bigger boat slide. We need a lot of material in order to satisfy future demand. On the left-hand side, you have the number of new mines, and that's for the future for electric vehicles. Why this is important is because really at the end of the day, they use the same materials for electric vehicles as they do for DoD, with some exceptions for electrolyte additives and things like that. But for the most part, you're still talking nickel, manganese, cobalt, lithium, graphite, and other major classes of material. The big issue here is that we have a supply-demand problem. Our projected cathode supply, there's a huge delta between that and the anode supply as well. So we're well under the future demand in North America. So we're going to need to accelerate that in order to create a domestic and friend-shored battery supply chain for both DoD and for electric vehicles and other markets. So this area specifically I want to talk about is the upstream. This is an area that ultimately is a huge gap in the United States. We don't do mining well. Regulations are really challenging, and we just don't have a great history of it. But there is a lot of interesting work in us doing that. We have varying degrees of different materials, and you don't really get to control where raw materials production ultimately is held, because that needs to happen where that material is. But where you can make a really big impact is in materials processing. This is an area where it's obviously less geographically limited, and so this is something that China has done for decades now really well, and is an area of future effort, I think, within the U.S. government on how we can create a better footprint in this particular space. This is sort of the main area of gap, which leads to downstream supply chain dependence on foreign entities of concern. I'm going to talk about recycling, which to folks might seem out of place here, but battery recycling and raw materials mining, those two have a lot more in common than most people think, right? At the end of the day, the challenges with battery recycling and the challenges with materials mining from virgin material is really separation science. So using some process, if it's electrical, magnetic, using different filters and different technologies to separate out the elements, and then refining those elements into a useful product. Both of those have a similar story and a similar way to do that. So I'm going to talk about recycling in the context of materials processing. So the three major classes are pyrometallurgical, hydrometallurgical, and direct recycling. These are areas that ultimately we are, as it goes down, this is the way lithium-ion batteries are made. Each of these are a higher value process that allows for integration into the battery supply chain at a later stage. So less energy intensive and more value. That's really what drives a lot of this. So pyrometallurgical is smelting, and hydrometallurgical produces a salt, which plugs directly into the cathode production. And then direct recycling is actually recovering material at the cathode level. So not making a new material, but taking the old material, repairing it, and then reintegrating it into new batteries. This is really important because the constituent materials, so the elemental value of each of these cathode materials, varies widely. So LCO, lithium cobalt oxide, about 70% weight cobalt, that's less important to direct recycle. But if you look at LFP, which is the future of a lot of demand for lithium-ion batteries, the elemental value is incredibly low. So doing that economically really needs direct recycling. Direct recycling, however, is not a single process. Direct recycling is a series of processes because before you can get the cathode back, you need to separate out all of these materials, the electrolyte, anode, carbon black, and then you need to re-add lithium because that's where the lithium is stored, is inside the cathode during the manufacturing process. And so really at the end of the day, that's a big challenge for lithium-ion battery recycling, is that you need to do all of these steps before you can actually direct recycle that material. There's a lot of interesting work going on at the national labs and in industry to try to do that. Ultimately, the question of how we do this economically is really being driven by scrap, and the way that we can ultimately take that and make it economical is by looking at the closer you are to the front steps of battery material where you're getting some scrap material, the easier it is to make that economic, because then you have less separation processes to do in order to do that. So lithium production, this is the area that probably in the United States we have the most promise. We have rich lithium resources in clay and brine, and about average in spodumene, as we understand it today. But Australia is the #1 producer. It did not used to be this way. This is a product of Chinese market investment into the Australian market, which is why you can see in this what's called a Sankey diagram, China controls a huge portion of the refined process. So even though they don't have a lot of lithium, they've invested in foreign countries, which have allowed them to control and drive this market in a major way. And so major market is Australia. That's rock-based resources or spodumene. And then you have Chile, Argentina, and that's where you're going to see some of these brine resources in the Atacama Desert. It makes a big difference what type of feedstock you have. These are all different CO2 emissions based on the material. So the least environmentally intensive is brine production, but the problem with that is you can't really scale that with demand, because brine production requires the sun to evaporate these ponds, which takes 5 to 7 years. With spodumene, you can scale up production much, much faster. And next we have cobalt. Cobalt is primarily exists in the Democratic Republic of Congo. This is just where most of the reserves exist. But if almost all of that production goes to China, again, you'll see refining in China you'll see it throughout this presentation on supply chain. This is a major area for the US to try to catch up. But ultimately, rest of Asia, rest of world, these are the two areas that exist. But ultimately, we have to figure out a way with cobalt. Recycling is a good way to get cobalt in our supply chain, but ultimately also to figuring out a way to work with the DRC on more environmentally sound and humanitarian means of production, and moving that supply chain away from China as much as possible. Next, we have nickel. Nickel is something that, if you asked us 8 years ago, we have plenty of nickel, but the type of nickel really matters. Ultimately, for batteries, you need very, very pure materials. Any material impurities, they typically are, what they do is they create areas for degradation of the electrode, and that is challenging because that decreases the life of the battery. So you need very high purity materials for all of these precursors. The challenge is the way the supply chain for nickel exists today is for class 2 nickel by and large, but class 1 is becoming a major driver, and will ultimately, if you look here, battery precursors are moving from 7% to 41% over the course of the next 15 years. And so it's a huge jump for what is a major area. So the US, unfortunately, is not very rich in this or in cobalt. We have some, but not enough to satisfy demand. So a lot of this demand is going to need to come from some of the French short countries like Canada, Australia, and Indonesia as well. So next you have battery components, so the cathode itself. And we in the United States are a very, very small amount. This comes from the 100-day supply chain report, which I wrote when I was at DOE. And this is the evolution over time of how these materials are going to be part of the supply chain. So this is evolving, right? So when you're talking about how much lithium do I need, that is driven by how many batteries you think you'll need, but it's even more challenging for some of these other materials. So trying to decide how much nickel you'll need versus how much manganese you'll need, depending on the size of the NCA market in 2030, these are some of the challenges that you'll see in some of the supply chain ebbs and flows on prices. This creates a lot of market uncertainty. Where China is very good at stepping in is they just prop up that market as prices go down, whereas in the United States, that causes investor heartburn, and a lot of these projects end up stalling because of that. So where cell production exists, this is an area that we in the United States have a decent cell production area. We're the second largest country in production. If you look at Europe as a block, we're almost as large as Europe today. And the three major markets for cell production are China, US, and Europe. The automotive OEMs typically like to make cells close to where they sell the vehicles. So you'll see the supply of cells closely line up with the percentage of the market share of electric vehicles. And so that's a pretty easy correlation to make. And the cost of sending cells across the world is higher than, say, the precursor materials to make those materials. So that's why you see a much more even distribution of battery production, cell production throughout the US now, or throughout the world. Now, granted, this doesn't heavily impact DoD because DoD does not use automotive grade materials and cells or automotive grade cells. A lot of the cells that DoD relies on come from China, largely because these sort of lower tier manufacturing materials, which if you remember this slide, a lot of the demand is coming from these major facilities, but they don't supply to these markets, right? They supply expressly for the light duty battery market, which is why you need an ecosystem in the United States for some of these smaller markets, because it allows for a sort of scale up of these markets and us to have a footprint in those markets without being completely exposed to the supply chain for China. And so, yeah, as I mentioned before, you can see China has a very large material processing and refining footprint on all of these materials. It's where they invest heavily. And then on the cell side, it's less so, or it's closely aligned with where the demand is overall. But their footprint in mining is less certain because of the fact that it's based on where that material is ultimately. So really quickly, I'm going to run through some major programs in the Bipartisan Infrastructure Law and the Inflation Reduction Act that are driving the demand here in North America for electric vehicles, batteries, and the battery supply chain. So when I was at DOE, we managed the 40207B and C grants. There's $6 billion. About $1.5 billion is left of that. DOE has not come out with what their plans are for that in the new administration, but there is money available in statute to do large-scale demonstration and first of its kind commercial facilities for battery materials and precursors, as well as battery cells and recycling facilities. And the IRA was passed. There was a few different tax credits. One is the 30D tax credit, which allows for new vehicles to use the critical mineral that have critical minerals, and the battery components, they'll have sourcing requirements in order to meet and get that $3,700, 3,750, ultimately 7,500. None of the material can come from a foreign entity of concern for eligibility here. And ultimately, this has caused a lot of supply chain challenges for companies to actually qualify for this. Yeah, that's how the calculation is done. And a lot of companies and a lot of the automotive OEMs tried to find workarounds in order to do that. And this is the way that the calculation of the percentages for the value go into this. I'm just kind of trying to rush through so we can get to questions as well. The other big one that people don't talk about enough is 45W. 45W is the leasing, what I call the leasing loophole. It has zero sourcing requirements, and it's caused a huge shift in leased vehicles to purchased vehicles for electric vehicles. So it's a huge change, which allows for $7,500 without any sourcing issues or income requirements. These are all things that are likely to be changed over the course of the next year as Congress is looking at different tax policies. Next, you have the 45X overview. This allows for 10% of the production costs of electroactive materials, which includes all of the materials I was talking about earlier, and then 10% of the critical minerals extraction and processing. From there, you have a $35 a kilowatt hour cell production credit. As I mentioned earlier, this was something that already existed in the United States, and so we have this pretty large credit for cell production, but we do not have much for the upstream, so the critical minerals and materials, which is my main focus at SMI and a coalition that we manage called the BAT Coalition. So we're looking at ways that we can change these credits to get to a more uniform incentive structure in the United States for cell and materials production. If we're successful at getting the 10% raised to 25%, that's really what we're looking to do, which would allow for the critical minerals and electroactive materials to go from that number that it was before, 2 and 350, all the way up to 10 and $12. And yeah, with that, I will conclude and answer any questions from the group.
That's great, Sam. Thanks for the great presentation. We do have questions coming in. If you've got questions you'd like to ask of Sam, please just enter them into the question box on the side of your Zoom panel. So they're coming in, and it's all across the topics you covered. So let's just start from the top. I'm very interested in the low temperature batteries. Are those that operate at minus 40 degrees Celsius, are those commercially available? And what DoD points of contact offices, organizations would you recommend for someone interested in that?
Almost every DoD office, because it's in a lot of the mil specs, almost every DoD office is looking at that does batteries is looking at low temperature performance. So folks that do work in the Arctic would be where I'd point people. Army, Navy that has low temperature performance. There's not off the shelf, as I understand it, and it depends on what scales we're talking about. It doesn't exist without what DoD has done in a lot of these applications is use heaters to keep the temperature at those when it's that cold to be able to qualify and have the performance needed to utilize that platform.
All right, next question. Are there export controls on cobalt and the other heavy metals that you talked about to prevent or at least to delay the depletion of our sources?
No, there are not export controls as they exist today. Most of the batteries for end of life end up going to developing countries. This is for both consumer electronics and other applications. End of life EVs in the United States go a lot to Eastern Bloc countries where the gas is really expensive. And we don't really have policies or uh, systems in place to capture that material back into the supply chain after it's been exported.
Okay, next question. What are the limitations, if any, for large-scale lithium thionyl chloride batteries?
Uh, well, one of them is thionyl chloride from a recycling perspective is very, very challenging. Most recyclers need to be specially equipped to handle some of the volatiles that exist in thionyl chloride. Thionyl chloride is also primary battery, so obviously single use only, but high energy density. So there's that. So I think they have a specific application in DoD, but widely, obviously, limits without the rechargeability. There's limitations on thionyl chloride chemistries.
Are there US-based small form factor drone battery manufacturers that you're aware of?
It depends on the scale you're talking about. There has been some major headlines on drone manufacturing in the United States, and there was recently a company called Skydio that produces drones that supplies to DoD. They, had their exports from China to the U.S. Sort of flagged as not available, and this is something that I think DoD is tracking well and recognizes is a gap. But as it exists today, there's not great production specifically for the drone applications. There are companies, a number of companies that are in the small scale space, and by small I mean 5 GWh and below, that I think have promising technology and really good material. But ultimately, there's not a huge production today to supply DoD.
Can you talk about the effects that repeated recharging has on lithium-ion battery life, and how do you determine the shelf life of a lithium-ion battery?
So as you charge and discharge a battery, what ends up happening is I talked about the coating, solid electrolyte interface. Uh, that creates a reservoir where lithium gets trapped and is unable to cycle and through the performance of the battery. So a lot of times that's what drives the decay of lithium-ion batteries and the capacity fade is that loss of lithium inventory on the anode side. Um, Shelf life for batteries, it really depends on the state of charge. If you were to charge a battery at 100%, what you would have is a dissolution of the cathode into the electrolyte, which would cause some issues on shelf life. But typically, 30% is what the air, or I think it's UN or one of the other groups that has a 30% requirement. It's the DOT. They have a 30% state of charge requirement, and that helps with the shelf life. But ultimately, eventually that battery will start to self-discharge, especially if you don't have a uniform solid electrolyte interface. So silicon and lithium metal both are reactive in electrolyte as opposed to graphite, which forms a stable solid electrolyte interface.
You talked about commercial supply chain, DoD supply chain. The question is, to scale up and drive costs out of DoD batteries, how dependent is DoD on the commercial EV side of manufacturing? And can DoD scale up its own manufacturing separate from those commercial EV applications?
I think it's very dependent. I think anyone you talk to in the DoD side, from Title III to IBAS, um, they all look for commercial applications, largely because DoD is not a large enough customer to supply at large scales. A big part of the challenge with DoD is that they are in a variety of different form factors. A lot of primes have very specific needs, which is a challenge ultimately for can DoD supply its own batteries and not have to rely on the electric vehicle market or be able to completely sustain without that. Ultimately, a lot of these things from you know mining to refining to producing material all of that needs to be at a certain scale in order to be economically viable. Otherwise, costs get very prohibitive for DoD to supply. So I would say if money is no object, then sure, theoretically DoD could do that. But even then, you're looking at less combat readiness because a lot of the innovation is being driven by electric vehicles, which means the materials are coming from those supply chains that ultimately are going to create better combat readiness for soldiers.
Got to go speed round now so we
All
get
right.
to it into. If battery production, and these are hard questions, if battery production is a commercially viable endeavor, why are subsidies being sought?
That's a great question. I was at DOE when that happened, so no comment on how and why the $35 a kilowatt hour exists as a subsidy today.
Are most cells for domestic EV battery plants imported or are they made here? Where are they imported from?
The cells are made here for the most part. Most cells for domestic EVs are made here.
Where would you direct people if they're looking for mil spec requirements for lithium batteries?
Each major battery has its own mil spec, so you can look, so 2590, 6T, those are major platforms. The CWB, they all have their own mil spec. So if you just Google CWB mil spec, you'll be able to find that. That's unclass.
And then last question, what's the one biggest thing you would have us do to reduce risk in the lithium battery supply chain?
I think we need to do two things. One is keep investing in the supply chain, invest specifically in materials refining and processing. And then we need to protect our supply chain from China, whether that's from an insurance policy that companies can buy into that would allow for them to keep building out capacity during price shocks, or it's tariffs or some other policy that creates barriers for Chinese material to get into the United States. But we need to be able to create this as this scales up. So we need to have a balance of when are we realistically able to supply our own market. Otherwise, we're going to end up with supply chain shortages if we cut these supply chains off from China without being able to stand up an alternative overnight.
That's great. Thank you, Sam. Sam Gillard from SMI for that great battery presentation. And I want to thank everyone for their attendance and the great questions. We're going to be posting this recording online as soon as possible. If you have any feedback about this event, especially topics you'd like to see us cover in the future, please email us at eti@ndia.org. I want to take this opportunity to highlight a few ETI upcoming events. The next Tech 101 will be in March on unidentified aerial phenomena, UAPs. So be on the lookout on NDIA website's calendar of events for more information. We're having a symposium at George Mason University's Arlington campus on February 28th. It's on the power of prototyping, where we're going to release a paper we jointly wrote with George Mason on how DoD can do its prototyping programs better to make them transition more effectively and gain more industry interest. Registration available is at that web URL listed there and at the QR code. And finally, make sure you're listening to our Emerging Tech Horizons podcast. It's available on YouTube and all the other typical podcast platforms. Guests include senior government leaders, industry leaders, NDI members. We do on-location episodes, and we're always looking for ideas about our future podcasts. To register for any NDI events or ETI events, always please visit www.ndia.org/events. Thanks again to everyone for joining us today.